Buenas tardes y gracias por acompañarnos hoy. En nombre de la Fundación Ecoscience le doy la bienvenida a la tertulia Arquitectura en Ambientes Extremos, Proyecto FIC Hábitat. Parte de la serie de tertulias colaborativas de Ecoscience que busca impulsar nuestra misión de conectar ciencia y sociedad, aportando al desarrollo del país mediante el intercambio de ideas y acercando la ciencia a la ciudadanía, labor que hemos realizado por más de 15 años como fundación. Nos encontramos en un momento histórico de la humanidad que ha dejado expuesto nuestras fortalezas y mayores vulnerabilidades como sociedad, por lo que la generación de conocimiento o la exploración de nuevas formas que permitan la resiliencia del humano y nuestras comunidades es algo clave. La ciencia puede ser un camino para luchar y adaptarnos a los cambios del clima y del futuro. Es así que nos encontramos trabajando colaborativamente con la Universidad Arturo Prat de Tarapacá en este proyecto. Quiero dejar a Karen Aviasa para contarnos un poco más de la iniciativa.
Hola Oscar, hola a todos los presentes que están conectados, a Michael también que va a estar invitado. Quiero presentarme, bueno, mi nombre es Karen Arriaza, soy académica e investigadora del Instituto de Estudios de la Salud de la Universidad Arturo Prat de Iquique. También directora del proyecto FIC Hábitat. Tarapacá se proyecta en investigación en ambientes extremos. Este es un proyecto FIC de financiamiento de fondos regionales del gobierno regional de Tarapacá y que está siendo ejecutado a través de la Universidad Arturo Prat, específicamente por el Instituto de Estudios de la Salud. ¿Ya? Este proyecto nace como una oportunidad para la región frente a la escasez mundial de estaciones de investigación en ambiente extremo. Lo que tiene como objetivo es lograr la habitabilidad de los seres humanos en otros planetas. ¿Ya? Y esta iniciativa del proyecto a futuro lo que busca es la factibilidad de instalar dichas estaciones de investigación avanzada en nuestra región. Esto dado a las condiciones o características con las que cuenta, tanto en el clima extremo que tiene nuestra región, la depresión intermedia, tanto en el altiplano como en el desierto, y el fácil desplazamiento además que tenemos entre una y otra. Es un escenario distinto a lo que se encuentra normalmente en las estaciones que existen en otras partes del mundo. Lo anterior va a responder a una oportunidad que se abre para la zona y también para la similitud de condiciones que podría haber en otros planetas, como el caso de Marte, por la aridez e inercia térmica con la que contamos en la región. Sin más preámbulos, quiero dar a conocer que hoy día la charla de hoy es producto de una colaboración interdisciplinaria que tiene nuestro proyecto, y es el caso del arquitecto que nos va a dar la charla de hoy, que es Michael Alan Fox, y que expondrá sobre su experiencia en el proyecto, acerca sobre los prototipos con los que estamos trabajando y también su experiencia personal en los trabajos a través de estos hábitats de ambientes extremos. ¿Ya? Quiero agradecer también a la Fundación EcoScience por la alianza que hemos generado, tanto en el proyecto y tanto como en esto de las tertulias científicas, porque dan a conocer también el trabajo que estamos realizando en la zona norte y poder difundir nuestra iniciativa. También quiero agradecer a todo el equipo de trabajo, a nuestra casa de estudio, la Universidad Arturo Prat, y obviamente a quienes nos financian y que nos permite hacer esto, que es los fondos regionales del gobierno regional de Tarapacá. Y con eso ya le damos el paso aquí a Oscar para que nos presente a nuestro Mike.
Gracias, Karen. Bueno, yo les quiero contar un poco sobre Michael. Él es cofundador y director de diseño de Foxlink Architects y es profesor del Departamento de Arquitectura de Cal Poly Ponoma y profesor invitado habitual de la Universidad Politécnica de Hong Kong. Su práctica, docencia e investigación se centran en la arquitectura interactiva y la intersección de la robótica y la fabricación digital. También participa regularmente en proyectos de investigación para el espacio exterior, cosa que vamos a poder conversar un poco en la tertulia de hoy. Fox recibió una licenciatura en arquitectura de la Universidad de Oregon y una maestría en ciencias de arquitectura del MIT en 1996 y ha enseñado sobre temas de arquitectura interactiva, conductual y cinética en MIT, The Hong Kong Polytechnic University, Art Center College of Design en Pasadena e Instituto de Arquitectura del Sur de California, en Los Ángeles, así como numerosos talleres internacionales. Bueno, le quiero dar la bienvenida a Michael y agradecernos por acompañarnos el día de hoy y podamos escuchar un poco su presentación, y luego de esto vamos a tener una sección de preguntas que pueden realizar en el chat en la página de CONECTA más FIC y vamos a poder tener una conversación al final de esta. Muchas gracias, Michael.
Hello, my name is Michael Fox, and I'm here to give a short talk about the FIC Habitat project. This is about architecture in extreme environments. I'm pretty excited about the project. It's one we're doing with Arturo Prat University and also with Cal Poly Pomona in Los Angeles, California. So I'm going to start off and just give a little short preview to some of the previous space projects that we've done here, and then talk a little bit about the project that we're doing with Arturo Prat. So I've been interested in space architecture for a long time, architecture in extreme environments. I think the vision that I have for extreme environments is that it's a model for how we can build on Earth. Basically, the vision is to make buildings that can survive on local resources, designs that can have very limited resources in extreme environments leads to a much higher respect of nature and the human being, and I think generates a strong drive to improve our lives here on Earth. So we can learn a lot from these extreme environments that can be translated to our normal terrestrial architecture on Earth. So there's a lot of valuable lessons that can come out of these extreme environments. I also just like architecture in extreme environments because they're cool. I think they generate a lot of really interesting projects, and the constraints are really difficult lots of times. So you're just playing off of some constraints. I'll start with this first project, which is one that we did at Cal Poly Pomona with students. I was the lead principal investigator on this project. This was sponsored by NASA. It was a deep space habitat. So with this one, we basically had to organize an entire program for 4 astronauts to live within this cylinder for about 7 months. And it was a pretty interesting project because they're in 0 gravity for most of the time. And so the space became very volumetric. Essentially, we have sort of the kitchen and the galley up here in the top. We have an exercise space next to that. There's a digital fabrication lab, a living area up here, that's the main one, and then hygiene. This is sort of for restroom and cleansing. We have 2 laboratory spaces, 1 and workspace 2, and then a control room. And all of this is within basically a cylinder. But then it's very volumetric, so there's kind of areas that you can pass through to go from one to another. Then we made this sort of full-scale mock-up in the parking lot at Cal Poly, which was pretty fun. And then we could like actually get inside of it and kind of test and understand the scale of ergonomics and things like that. So, you know, it's a high-res kind of, a low-res kind of foam mock-up of the interiors, but it was useful in understanding the real sense of scale to a lot of these issues. And then we had this other next project. This was also sponsored by NASA. We get to do a lot of projects for NASA because we're kind of connected here to JPL pretty closely, which is out in Pasadena. And there's a lot of really great researchers there who can give us feedback and input. So with this project, we made a handhold foothold. So if you're in sort of a extreme environment, you can kind of, or a 0G environment or low G environment, you can hang on to these things, or you can put your feet under them. And so we made this sort of, you know, right now they actually use Velcro straps. It's just a piece of Velcro and they slip your foot under it. They break and stuff, and there's no feedback. So this one has feedback generated into it so that when somebody is grabbing onto one or slips their foot under one, then that information shows up on the control panel. And there's also, you know, if one breaks or snaps off, there's an accelerometer in there that tells you if it's broken or if it's been damaged, which is also really important for monitoring everything on the ship. So we made one of these in a prototype, and that was a lot of fun. And then we were able to take this into zero gravity in Johnson Space Center down in Texas and fly and test whether or not the accelerometer worked. And you can actually see my shoe here on my foot, and I'm using one of the traditional kind of Velcro straps, and that's what you use for hanging on or keeping yourself grounded. So ironically, this photo shows what we were actually designing is a new version of these. So this was called Wii in Zero G because we actually used the accelerometer in the Wii, you know, it's a video game. And then we played the game and we were able to see the data from the Wii and compare that to the data from our accelerometers. You can see on the remotes, we basically like just Velcroed our accelerometers onto the Wii accelerometers. So we had a data set and we could test whether or not the accelerometers worked. And they did work quite well in zero gravity. They did not work in positive gravity, which was kind of interesting. Because when you're on these zero G flights, you get zero gravity, but then you also get like 5 Gs and you're kind of glued to the floor. And in that case, the accelerometer didn't work, which is pretty interesting. Anyway, that was a lot of fun. So this next project was a third project for NASA that we did just a couple of years ago. And this one was a habitat for Mars. And the idea was that, you know, how you could transport it, how you could transport this to Mars, and the astronauts could live within this capsule. And then once it arrived in Mars, it became the actual habitat. You know, traditionally, the vehicle that is being used for transport is not the actual habitat on the surface of the Mars. And so this was, the idea was exploring this idea that the actual transport vehicle would be the habitat on the surface. And so here's an image of a prototype. This was taken out to the desert in California. These were some early schematic designs because one thing is, you know, that it would not just be one cylinder, but it would be over many, many trips there, how it could grow into a larger sort of surface habitat. So these were some early models, some other different early models, concept designs. These are all done by students. And then this one was sort of the one that evolved as an initial concept. It was kind of like a roly-poly bug. So this was the model, and it essentially unrolled. So this diagram sort of explains what's happening is that phase one is the travel, and within this cylinder, there's actually 1, 2, 3, 4 of these sort of wafer cylinders. So the larger cylinder is sliced into 4 of these. And then these are able to, once it lands on the surface, they actually have mobility so that they can roll across the surface to a flat, sort of relatively good landing space where they want to set up the habitat, and then actually unrolls and becomes the habitat. So this kind of explains that a bit more. So you have, you know, this habitat is the rocket ship, and they live within this space while they're flying there for, you know, approximately 7 months. And then once it lands, these guys can roll to a space and then unroll like this. And we did origami studies to try and like explore how this could be very compact. Essentially, the program is like this. You have a hygiene area, you have bedrooms, you have a gym, you have leisure and conference room for teleconference. You have a hydroponics greenhouse, you have a laboratory, we have a medical bay, and a control room and life support. Now, when these are completely rolled up, you can live within them. And so in that case, the circulation runs all the way along one side, and all of the habitat modules are pushed off to the other side. And so you kind of have a corridor that runs down the side. So these are the kind of layout in plan once it unrolls. And for this, we made a fully detailed virtual reality model. And this was in the rolled up position and in the unrolled position so that we could put on VR glasses and walk around through the habitat and make different design decisions. You also, you know, we kind of rendered it low res, but we had all of the modules, et cetera, within there, including things like furniture. And it was really helpful to kind of understand, you know, head clearances and how large furniture and the other equipment would be. And then we also made a full-scale chunk of the prototype, and we used augmented reality. So using not just the VR model, but the AR model, and we had this mapped onto a very large scale, full-scale mock-up. And the mock-up was pretty low res, but once you put on the AR glasses, you would really be in the full-scale environment. And that was really helpful. That was actually more helpful than the VR model in really kind of understanding the details and the sense of scale of this thing. Then we also worked on a lot of small-scale robotics on how this thing would unroll, how it would move in terms of mobility. These are some of the smaller robotics models that we did. This one would roll, this one would unroll. And then, you know, making some pretty detailed drawings. So architectural drawings of the scale of this, you know, in plan and section, and understanding the relationship of the spaces to each other. These are some other architectural drawings. And then we made this, this is basically 1 to 10 scale prototype. So it's a really big prototype, not a really big prototype, a very big habitat. So if you imagine this is 1/10 of the scale, the habitat is actually quite large. It's a little hard to get your head wrapped around how large this thing actually is. So this is the 1 to 10 scale. And this was used to explore the kinematics and the mechanics and other different, anyway, this was a version of this prototype. This is right outside, you know, in a parking lot. And basically, you get a sense of the scale of the prototype. It was pretty valuable. We then took this prototype out to the desert to place it in an extreme environment. And we unrolled it out there, basically, so you could, you know, the whole thing would just kind of unroll. And it had a secondary transformation. Once it unrolled, then the sides kicked out to make this thing more volumetric. And, you know, so it's a little more like, you know, a blown up balloon, and the atmosphere is basically pulling on the exterior of this thing. It's so, you know, it's actually, you know, the inverse of what we normally would think of here on Earth, where you would try and mechanically unroll this thing. Here you need to constrain it so that it doesn't unroll very fast and, you know, just like spring open with the pressure that's inside of it. Kind of think if you take a bag of chips up to the mountains high, and then the bag of chips gets really puffed up tight. And so it's kind of the same idea with this structure. And so it's a little bit, you know, it was a little bit in terms of kind of understanding the physics for architecture students and how, you know, things are different and how you can reconcile those constraints. So this is another project that I did with students in terms of a pretty extreme environment, which was a habitat for a space elevator base. So if you don't know about the space elevator, it's a theoretical idea. It's actually pretty realistic. We just don't really have the materials developed at this point to be able to span that far. But the idea is that you essentially have a cable that goes from you know, a place on Earth, and this would be an equatorial place somewhere around the equator in the ocean. And then it would be basically a string that goes up to a point in geostationary orbit. As the Earth is rotating, this point is rotating with the Earth. And, you know, most of our expense and danger is involved in getting stuff through the atmosphere. Once you're past the atmosphere, you know, it's pretty affordable to kind of push things and they will keep going. So, you know, the idea with the space elevator is pretty interesting. And there's a lot of proponents. It may happen someday, but, you know, the likelihood, you know, it's probably pretty far off, and it would probably happen, you know, with using carbon nanotubes, which are possible, but they're in their infancy right now. I think we can just make, you know, very millimeter lengths of carbon nanotubes, which would be the only material that we know that would be strong enough to make a space elevator. Anyway. So the idea for this was not about the technical issues of the space elevator, but it was to make the sort of architectural base for the elevator. We looked at a lot of biomimetics in this studio, looking at kind of forms that were with nature. So this is out in the ocean, and the elevator is sort of coming out of the top of this. This was another version. These are teams of 3 students who would work on these projects. And so this was another one that here you can see it out in the ocean. And basically this was kind of like a whole habitat that was self-sustaining. And that was one thing, is a little more self-sustaining in that it was sort of a closed ecological loop within this thing, in terms of being able to grow with hydroponics and being able to, you know, recycle a lot of the waste, etc. In these habitats. This is a different project, which is a space-based solar habitat. And with this project, we were looking at space-based solar. So the idea with this is you make a massive solar panel up in space that beams this energy back down to Earth. And you know, it sounds kind of crazy scientific, but it's pretty interesting as a proposal. And, you know, there's a lot of proponents who are very interested in this idea, because, you know, you would get massive more amounts of energy through this space-based solar power idea than you do by simply having solar panels here on Earth. By the way, it's the solar is beamed back to Earth with microwaves, and you set up kind of a field of cables to you know, harness that microwaves back on Earth. But once again, we were not so much utilizing the space-based solar power as a design project as we were looking into the habitat for people who would be living on the space-based solar space station and working to fabricate this thing. So we were looking at the habitat, and the project basically had, you know, 5 considerations: the actual trajectory issues, like how to get the materials to space, the building materials; looking at space manufacturing, how we would fabricate and assemble and construct things in space; and then human factors, you know, things like ergonomics and programming, like the relationship of spaces, which you see here, you know, in like a bedroom space. And then safety and growth, you know, how this thing could expand and be larger, you know, once it's already, I didn't want that to be in the video. Anyway, so these were the primary considerations: the trajectory issues, the space manufacturing, making stuff up there in terms of materials, 3D printing, etc., and then assembling and constructing things in space, as well as the human factors of ergonomics and programming. And then safety, keeping people safe is the #1 priority. And of course, growth, like how this thing could be adapted and how it could grow and expand over time. And then, you know, so these are a few of the different designs that were created. You can see the massive solar field, and then the habitat. This one actually generates a certain, I don't know how many G's, but a certain amount of gravity within the habitat. This one has these sort of round pods as the habitat. And this one was sort of a collection of cylinders, so vastly different approaches to the habitat. And again, they were all looking at, you know, issues of adaptability and expansion as well as construction. So these kind of informed the actual designs. They were not just form making. And here's another one, which is pretty interesting habitat design. And one more here, which is kind of a large collection of these like little modular cylinders, pretty interesting. And, you know, they looked at different interiors, etc. This is one last project I'm going to show you, which was an economically viable space station. And the student looked at lots of different, you know, ideas for space tourism and different space tourism proposals. I think a heavy emphasis was placed on the programming to make something that was commercially viable and economically workable, you know, for tourists to go into space. And so there were, you know, the same issues in terms of, I suppose, constructability and how this thing could be constructed in space, and how, you know, you could manage your resources of waste, of food, of energy. All of these were, you know, critically important. This one sort of grew in terms of adaptability along the hexagon grid. This was another one, sort of a twisted helicoid type of shape. And, you know, we looked at different types of interiors, etc., that could happen within there. Another one, which was, you know, pretty interesting interiors, how these interiors are interpreted, what type of spaces. More crazy one with hexagonal sort of shapes that are, you know, but that are framed in with different panel systems. But, you know, it actually was really interesting, like simple solution. It's very small here, but simple solution for adaptability and expansion, which was extremely modular. You could just put these rods together into 3D hexagon shapes, and then you panelize them. And so this could be pretty easily expanded over time, you know, and these are the kind of spaces you get inside, but it was a good sort of exploration and constructability. I think that's going to end it for more. There's much more that we're going to talk about in terms of our project for the extreme environments, which is this extreme environment habitat. And basically, we're going to look at developing this habitat, which originates in the opportunity of the region, in front of the shortage of research stations in extreme environments. So the idea is to develop a working habitat that many other people can come and they can rent and they can use and they can do research. And it's actually, you know, the idea is that it is built in an extreme environment. And so, you know, it's something that could be built and owned by the Habitat project, but it could be used by many others, and it could be very valuable. So I think the general aim here is to determine and prepare the necessary conditions and requirements for the design, and you know, place it in the short or medium term of scientific stations for habitability and for self-supportive sort of extreme environments. And this could be very valuable in positioning the region as an axis of scientific development. and technological sort of development within the country. And, you know, it would be open to international researchers. It would be open to the world. So additionally, I think the dissemination, the motivation and stimulation of this interest in the science community and in the regional community and in the eyes of students, there's value that crosses a lot of spectrums for this project. So I'm pretty excited about it. I think we have sort of 6 primary considerations for it at this point. One is the spatial optimization, you know, how we can be very efficient, not wasted space. The other is all the human factors, including the ergonomics and the programming. Thirdly is the safety of people, protection from the natural elements. Fourth would be the resource utilization, basically that it's a closed loop system. Number 5 would be construction, how you can fabricate and assemble and construct this thing. And lastly, transportation, because you may even want to transport it there, assemble it, leave it for 6 months and move it to a different location. So, you know, the transportation is very much tied to the fabrication and assembly of this design. So the idea is that we demonstrate a mass balance of resources and the waste that are required for the humans that are living in extreme environments. And so it covers a lot of really interesting issues of materials, of connections, of human interactions. All of these can be explored within the space. Here you see sort of an extreme environment of the International Space Station. And so these are sort of where we're at now, that the total capacity will be for 7 people, 4 males and 3 females. Living space enough for 7 people. And basically there's a table here that works out the adjacencies of the different spaces. We have dining room, kitchen, a recreational zone, an exercise area, a lab facility, nursing area, communication equipment area, and then men's and women's bedrooms, men's and women's restrooms, men's and women's shower room, and then a supply or pantry, an area for crops or hydroponics, and an area for recycling and trash. And we've been through a lot of these habitats in the past. It's pretty minimal. It will be pretty tight environment. So one thing is really kind of really fine tuning this programming and how things are worked out spatially next to each other. Again, here's sort of those factors, the key factors that we went over of space optimization, human factors, safety, resource utilization, construction, and transportation. And those are all things we're going to kind of critically look at, and that will inform our design. Anyway, thank you very much. This has been kind of an overview of some of our work, my work with the university and work with NASA and extreme environments. And I think a little bit of a preview of the Habitat project we're doing with Universidad Arquitectura Pratt. So thank you so much. I appreciate it. Bye-bye.
Bueno, muchas gracias, Michael, por tu presentación el día de hoy, muy interesante. Queremos compartir un par de preguntas ahora contigo para ver si podemos quizás meternos un poco más en la conversación. De lo primero que hay un par de cosas, de los ejemplos que mostraste hoy en tu presentación, ¿cuáles en tu opinión se podrían construir efectivamente próximamente y no en 20, 30 años más?
Michael, now we are going to have some questions. The first one is, which of the projects mentioned are more feasible or more possible to be built in the near future?
First off, hello. I'm wearing the same shirt. I think probably the Cal Poly project, which was the Cal Rolly, which was the project that was for Mars that unrolled and then made a series of habitats. And I think probably just because we worked it out to a fairly high level of detail, and that was with an entire year of students. Over 60 students worked on that, and it was with me and Professor Mark Schulitz, who also worked with the design studio, and another professor in engineering who worked with us as well. So we worked it out to a fairly high level of detail. I think the one thing that was frustrating was that on Mars, as I mentioned, the pressure would actually pull it open. It would spring it open. And so the mechanics on Earth were necessary for opening it. But on Mars, they would be necessary for actually constraining it to slowly allow it to open. So that fundamental difference, we didn't really look into in terms of the pneumatics fighting against the mechanics, which I think would be, pretty interesting to work out. Sorry, that's long to translate.
Sí, bueno, creo que el proyecto que desarrollamos con Poli, el cual se desarrollaba, sería el que está con más probabilidades de poder desarrollarse. Precisamente porque funcionaba con muchos detalles. Él menciona que se trabajó un año entero con 60 estudiantes, con él y también con un ingeniero y otro profesor. También menciona que la parte más frustrante era que mientras en la Tierra la presión lo abriría, en Marte funcionaría en una forma opuesta. Go on.
Súper. Mira, otra de las preguntas que en realidad me pareció muy interesante en el inicio es que tú mencionabas que la arquitectura de lugares extremos podría ser beneficiosa para la naturaleza. ¿Podríais desarrollar un poco más esa idea y quizás compartir con nosotros concretamente cómo ese escenario podría beneficiarnos a nosotros como humanidad?
Michael, there's another question. It says, you talked about that extreme environment architecture could benefit nature. Could you develop on that idea?
Sure. I'm always interested in this idea with the space architecture, the idea of bringing it home, meaning that these are futuristic projects, but they could be a model, I think, for how things could be designed or how things should be designed here on Earth, in that they're very efficient in their resource use, efficient in their spatial optimization, and typically they're closed loop systems, meaning that all the resources are contained within the habitat. So there's like this mass balance of the resources and waste. And I think lastly, another thing would be that we always look at constructability that includes adaptability so that they can be added to or they can grow over time.
Muy bien. Bueno, básicamente él dice que le interesa mucho la idea de la arquitectura del espacio y para poder traerla o adaptarla a la Tierra. Puede haber un modelo que pueda ser tomado desde el espacio y pueda ser adaptado a la Tierra. Por lo general, estos son sistemas ecológicos cerrados. Todo está contenido en el hábitat y por ende hay un muy buen balance entre los recursos y los desperdicios. Siempre estamos buscando poder adaptar esta constructibilidad con adaptabilidad. Eso. Come on, please.
Oscar está silenciado.
I can't hear Oscar.
Ahí sí, sorry.
Yeah,
Entrando un poco más hacia el proyecto Hábitat y lo que comentabas en torno al proyecto acá en Chile, ¿cuál es el tipo de infraestructura y su relevancia en temas de adaptabilidad que se busca generar en el desierto, principalmente por lo que vi en tu presentación? ¿Y tú piensas que en algún momento esta investigación o estos escenarios que se van a construir podrían tener un impacto en el día a día de las personas?
The third question, Michael, was what is the type of infrastructure and the relevance to adaptability issue that the Atacama project seeks to develop? And could it have an impact on people's daily life?
I'm not sure what is meant by infrastructure, but I think it's similar to the last question in the balance of resources and waste, meaning that if you can grow hydroponics, grow food within the place, if the water is completely recycled, if 90% of the waste, including like human waste, is recycled, it can help to look at ways for demonstrating how the resources can be used very efficiently and reused and recycled. And I think that's a really important part. And, you know, the other is social issues, you know, how people can actually live very closely together for long periods of time, and what type of different spaces are needed or how spaces need to be separated. I think those issues are also really interesting to study in an environment like this.
Ya, bueno, primero menciona que no está seguro mucho de lo que quieren decir con lo que es infraestructura, pero más o menos entiende que es una pregunta similar a la anterior. Y lo que menciona que es muy importante, hay dos cosas importantes. La primera es poder balancear los recursos y obviamente los desperdicios que se generan en el hábitat. Por ejemplo, da el ejemplo de los cultivos hidropónicos y también de reciclaje, que sería interesante que obviamente estos cultivos podrían utilizarse con agua reciclada y también que todos los desperdicios que generan los seres humanos obviamente se pudieran reutilizar o reciclar. El segundo punto son los temas sociales, obviamente, de interacción, que significa vivir con otros seres humanos en el espacio que se les da, y también poder pensar en los espacios separados que cada ser humano necesita para poder cohabitar sanamente.
Genial. Mira, yo creo que entrando quizás a las últimas dos preguntas, hay una acá hay una un poco más técnica que indica específicamente cómo funciona la aislación térmica en tu hábitat desplegable y sobre todo en el tema de las murallas que son que se pueden doblar finalmente.
Yes. Next question is, how would thermal insulation work in a deployable habitat with foldable walls?
That's a good question. I think, you know, there's a lot of expandable types of insulation that could simply be in the walls. So, and that if the walls are fixed panels and they fold origami style, then there's no compacting of the insulation. If it's something where there's actually creases in it, then maybe the creases are something that's rigid, that doesn't compact and degrade every time it's folding and unfolding. And then the panels themselves could simply be fixed panels. So they're not constantly being compressed and decompressed. That makes sense.
Sí, muy bien. Dice que es una muy buena pregunta. Que hay distintos tipos de estos sistemas para poder generar lo que él llama la insulation, ¿no? Si son fijos, no va a existir una compactación de este sistema. Y si hay pliegues que no compactan, se pueden degradar, por lo que también se deberían volver fijos. Dice que es algo que es discutible la pregunta.
But I should say that with the Atacama project, that's one thing we want to look at, is so it can be transported from one place, maybe folded, put on a truck, taken to another place and deployed again. So that foldability or deconstructibility is going to be really important.
Sí, él dice que justamente esto fue algo que ellos quisieron investigar a través del origami, ¿no? Del origami. Justamente querían ver esto para que estos hábitats puedan ser tomados y transportados a otro lugar. Querían investigar justamente ese factor del hábitat, que pudiera desplegarse, pudiera doblarse.
Súper, gracias. Y yo creo que quizás entrando a la última pregunta, que quiero juntar dos, principalmente es cómo un arquitecto termina trabajando en la creación de hábitat extremos, y también si nos puedes contar un poco más sobre cómo es tu proceso de trabajo desde el diseño arquitectónico, pero también tu trabajo colaborativo e interdisciplinario con científicos, ingenieros, en el diseño de estos hábitats en particular.
As the last question, Michael, would be how you end up working in extreme environment habitat. And also he would like to know how you work, how you design this habitat.
I became involved in space architecture a very long time ago at Cal Poly through a guy named David Nixon, who is a great space architect, and slowly began to get introduced to many people at NASA JPL who always came out to studio, who began working with us on a lot of these projects. And I showed a lot of them only kind of a few images, but we've done a lot of these projects. And I think it's always been interesting to me because of this model of efficiency and of kind of the balance of resources. And so I think over the years, you know, I've gained some knowledge because I'm a regular Earth architect, not a space architect. And when you see the relevance in space architecture is really very similar to extreme habitats on Earth. When we look at extreme habitats on Earth, you know, you have to deal with many of the same issues of living in isolation, of not depending on infrastructure, things like this. So I think it makes a natural translation to look at extreme environments on Earth.
Ya, bueno, él cuenta que se involucró hace mucho tiempo, habla del profesor David Nixon y también con algunas personas de la NASA. Y bueno, trabajaron juntos en muchos proyectos. Y obviamente lo que le interesa de este tipo, de esta área, es la eficiencia de los modelos, poder investigar la eficiencia de los modelos y el balance de los recursos que están disponibles, lo que hablaba antes de obviamente de cómo utilizar los recursos y poder reciclarlos. Obviamente durante todo este tiempo él ha ganado mucho conocimiento y experiencia, y él habla que la importancia de la arquitectura espacial es que es similar a la arquitectura o al desarrollo de hábitat en ambientes extremos, porque en ambos casos tiene que lidiar con los mismos temas, con las mismas limitaciones que podría ser en Marte y acá en la Tierra en ambientes extremos.
Gracias. En la última pregunta en general quizás no se entendió mucho, era ¿cómo trabajas o cómo es tu proceso de trabajo interdisciplinario, con ingenieros, con científicos que son parte del diseño de estos hábitats en particular, y cómo los integras a la arquitectura?
Okay, so there's one last question that has to do with how you relate with other experts in their different fields in order to come together and work on these extreme habitats. What is the process? What's your process?
That's a really good question, because not just for me, but a lot of the students are you know, familiar with architecture on Earth, but not necessarily extreme architecture. And we say it's drinking from a fire hose, meaning you're getting just tons of information at the start of every project, which is unfamiliar to you. On Earth, we always have constraints. You know, where do we place windows to get adequate sunlight? What type of insulation do we need? These types of kind of normal issues, but they're not extreme. And when you look at extreme situations, these constraints are much higher constraints on your design. So in a way, we rely a lot on engineering experts and, you know, the consultants who come to help us with the projects so that we can look at things like the actual constructability. We can look at the programming, the organization, the ergonomics, all of the human factors involved. But then there's a lot of extreme engineering issues as well that we work with the consultants and get their feedback. And there's a balance between, you know, what is going to work and what would be best in our vision of the architecture. So, so there's always this kind of feedback with engineers, but in the extreme environments, it's much more extreme than a normal building. Is that good?
Muy bien, es una muy buena pregunta, no solamente para él, sino para también los estudiantes. Todos se familiarizan con la arquitectura de la tierra, pero no con la arquitectura extrema. Él menciona que es como beber de una manguera de bomberos, ¿no? Es absorber mucha información. Hay muchos elementos a tomar en cuenta, pero en una situación extrema, en un ambiente extremo, estas limitantes son aún mayores en términos de diseño. Así que ellos confían mucho en los ingenieros, de hecho consultan con ingenieros para ayudar en los proyectos, en cosas como la constructabilidad, la organización, la ergonomía, factores humanos y problemas de ingeniería extrema. Entonces consultan directamente con ellos y buscan un balance entre ambas visiones, entre la del ingeniero y la del arquitecto. Hay un proceso ahí de retroalimentación constante.
Súper, muchas gracias. Y bueno, muchas gracias, Michael, por tu presentación y por participar en la tertulia del día de hoy.
Thank you very much, Michael, for your presentation and also for your talk.
Thank you guys very much for inviting me, and I really look forward to the project. It's going to be a lot of fun. It's going to be super interesting. So I hope to actually come there soon. So let's hope next time is not on Zoom. Anyway, thank you so much.
Muchas gracias por la invitación. Estoy realmente, para mí el proyecto es especial, muy divertido, muy interesante y espero poder la próxima vez visitarlos y que no sea a través de Zoom.
Bueno, muchas gracias a todos los asistentes y a CONECTA más FIiS y agradecer en especial nuevamente a Michael Fox por su presentación. Los dejo invitados a seguir nuestras próximas tertulias de EcoScience y por supuesto estar atentos al proyecto FIC Hábitat que próximamente van a estar avanzando. Y para estar informados de todas nuestras tertulias, los dejo invitados a seguirnos en nuestros canales digitales, Instagram, Facebook, Twitter, YouTube como ecoscience.org o ingresar en nuestro sitio ecoscience.org. Muchas gracias a todos.